This is the addendum material to the spinning symmetric top. And there's this obscure expression for the angular velocity that has three different systems of unit vectors in it. So I want to elaborate upon something we discussed in class today that can be done vectorially and not rely necessarily on the picture, because the picture can be a little misleading. It's just a snapshot. So let's have a look at the three Eulerian angles of the symmetric top. I've drawn these in advance so I don't embarrass myself by trying to draw them in real time. The first one, the top one here, is the top precessing. We know that if it has an axis here and it rotates around like this, it's rotating about the z-axis, and that's the z-axis in the lab frame. So the associated angular speed as this goes around like this is phi dot, and it is around the lab z-axis. If we have a nutation like this, we know that that is a theta displacement, because that theta is the same as the spherical coordinate theta. So the associated angular speed is theta dot, and that occurs about the line of nodes, which is an intermediate step in the Eulerian scheme. So it goes like this, like this, like this. And we have psi as the top spins. If you look at the screen, the top spins like this. There's a psi rotation, and it has associated with it psi dot. That's already around the z body axis. And the expression that you look at and say, well, why? That looks all mixed up. Looks something like this. Line of nodes, I'm going to call it lambda line. And then I have omega psi, zb hat. And we start with the way we did it in class, which is omega then translating each of these is phi dot k hat plus theta dot line of nodes hat plus psi dot, and then that's zb body. So this one, this body, we don't have to do. If we want this in terms of body axes, zb is already done. X body, y body, z body. Okay, because the expression for the kinetic energy is simple in the body axes because it's I omega 1 squared plus I2 omega 2 squared, I1 omega 1 squared, and so on. But what's accessible to us is not the internal angles of a spinning top. That's too complicated. What's accessible to us as we sit out here, and this is the general philosophy behind this and motivation, what is accessible to us are these Eulerian angles. So it's more or less this, two of them, the spherical angles. All right. So the way I wanted to do this is different than, I'm sure someone has this, I haven't seen it. So this is a little bit different. I'm going to do this with vector analysis rather than try to do the picture in 2 dimensions, because like I said, that's kind of, it can be misleading. So I'm going to start over here with X that corresponds to an I hat direction, and the Y, these are lab. And of course the Z is altitude for a right-handed coordinate system. And this is the J hat direction. And the first thing we do is rotate around K hat, which is out of the board. So this comes here by an angle phi, and this comes here. Now these are unit vectors. So I'll call this one X1 hat, and this one Y1 hat. So now I've just got fairly straightforward things. After the first rotation, I have a new set of axes. X1 hat, let's find that. You go out this much, which is cosine theta of X1. Remember, it's a unit vector, so I don't need a prefactor of any magnitude. Cosine phi, I hat, if I said theta, it's phi. Plus sine phi, j hat in the original system. Then I need y2, not y1. I have to go back, which is minus sine phi. That angle is the opposite side of that angle. That's phi 2. I hat, and then I have to go up this amount. So I have plus cosine phi j hat. And then z1 is just k hat. So that stays the same. So that's the first rotation in the Eulerian scheme. Now we do the second rotation. So think about what happens with the second rotation. You go around the line of nodes. The line of nodes for us is x1. This is what I called lambda 1 earlier, or just lambda earlier. That's the line of nodes. So now, if you would take your right hand and point it along x1, so x1 is, here's x1 on the sheet. Correlate that, please, in your head. Grab it with your right hand, with your thumb in the direction of x1, and that angle comes out like this. So right now, as it stands, here's x1, here's k, and we're going to rotate that back the amount theta. Notice that the pen is coming at my face. If this is the line of nodes, the pen is coming at my face, back. So if I were to drop a shadow, shine some light and drop a shadow on there, the rotation around x1, y1 hat, here is the shadow, and this length of this is, remember, this is a unit vector now, so I bring it back in amount theta. I'm coming back in amount theta. So x2 is along the line of nodes, which is x1. That doesn't change. Now y1 comes off the plane. So y1 is over here, z1 is over here, and I'm rotating around x1, which is over there. So I'm rotating back. This came off the plane. How much? Well, a lot of it stayed on the plane at this point. So that's going to be in that direction, y1 cosine theta. And then it comes up an amount z1 hat, which is just k hat again, sine theta. Now, the only tricky one, it's not really tricky at all, is z2 hat. Again, this comes back. It comes back. So the y1, so it's got a projection along here, which is the y plane in a sense, and it has a piece up. So I have here minus y1. Move that over. We'll move. Minus y1 sine theta. That's the projection here, and that's got a piece up, and that piece up is z1 cosine theta. Remember where cosine theta is? Cosine theta is here. So here's z1 cosine theta, and here's back. And then finally, so this is after the second rotation. We do our third rotation, and our third rotation is around z2. So z2 is here right now. Actually, we'll just and we'll just rotate it. Point our thumb in the direction and rotate it. So we have in that case rotation around z2, which is z body, because that's not going to change. So now I have x3 will be equal to, and if you think about what's going to happen here, I've got these guys just rotating around this guy right here. This was our, actually I have it back this way. So xy, and this is going to rotate positive this way by an amount psi. So now I have to go here and here. This is now the cosine of psi. This is psi, the angle psi. So I go up and over. So x3 gets x2 out cosine psi plus y2. So it's just a rotation in the plane. So this looks kind of like what happened in step 1. So this is x2, and I wave my arms around a little more in class, and you got the 3D effect, plus y2 hat sine of psi. And then I have y3. It's just the same rotation around the z. It's a rotation around the z-axis, is what it is. Positive angle. So this is minus x2 sine psi plus y2 cosine psi, and z3 is equal to z2. And these, because it's the final one, this is the third rotation, these are the body axes. So now I can associate them with the body axes. The rest of this is expanding one set of vectors in terms of another. You've heard me say many times how important I consider the principle of expansion of complete set. You do it in quantum mechanics with Brockett. You do it in electricity and magnetism. Think of the box with grounded sides and two sides held at fixed potential. You're expanding a complete basis set. The details and the sort of nuts and bolts of what's what changes from subject to subject, but at the end of the day, it's essentially the same form. Project, basis set, project, basis. Okay. So I'm going to stop here and move on to the actual projections.